Finding domains algebraically. So in a previous video, we talked about domains and ranges in discrete sets. We talked about domains being the set of x values and ranges being the set of y values. We briefly mentioned that with graphs, there were infinitely many points, so there were infinitely many x values, infinitely many y values. But we didn't go too much deeper than that. So let's talk a little bit more about functions and about their domain. So an x value is in the domain of a function if when we have the function in function notation, if we can plug that x value in with no problems. So an x value is in the domain if we can plug it in with no problems. So let's look at this function, f of x equals 7x plus, the square root of 7x plus 5 is -2 in the domain of f. Well, we can plug -2 in and see what happens. So f of -2, plugging -2 in. So we have 7 times -2 plus 5, all under this radical. 7 times -2 is -14. -14 plus 5 is -9. So we have the square root of -9 and uh-oh. 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 We have a negative under a square root, and that's not a real number. Not a real number. So when we plug -2 into this function, we get not a real number in return, which means that -2 is not in the domain of f of x. It's a really ugly box. There we go. Beautiful. So let's try something different. -2 is not in the domain. Is 0 in the domain of our function f of x? Well, once again, same idea. Let's plug in 0. So we have the square root of 7 times 0 plus 5, which is the square root of 5. Now, the square root of 5 is not a nice number. It's not a nice number, but it is a real number. We can't take the square root of a negative. We can take the square root of a positive. If you put square root of 5 into your calculator will shoot you out a decimal number because it is a real number. And because the square root of 5 is a real number, 0 is in the domain. When we plugged 0 in to our function, we did not get an issue. There was no problem. Square root of 5 being an irrational number is not an issue for us. It would be an issue if there were a negative, but that wasn't the case. So we can say 0 is in the domain of f of x. So the question then becomes, how can we determine what numbers are in the domain of a function just by seeing the function in its function notation? You know, -2 wasn't, 0 was. Where does that break happen? Where do the x values start working and where do they start not working? And that's what we're going to be talking about in this section. So let's scroll on down. Finding domains algebraically. We start by assuming that all x values are in the domain. So we start with this assumption, all x values are in the domain. And that would mean that the domain was -infinity to infinity. -infinity to infinity would be all x values are in the domain. We start with this assumption, and then we go about eliminating problematic x values. And there's only two problems we have to worry about right now. There's two big domain rules for now. There will be more domain rules later, but for now, just two. And here they are. First one, no x value in the domain should create a negative under an even root. And that was what happened up here. We had a negative under an even root. This is a square root, but same would be said of fourth roots, sixth roots, eighth roots. So an even root, this is going to be, square roots, fourth roots, sixth roots, and so on, any even root. Now, odd roots are okay to have negatives under. You can have a negative under a cubed root, and that's fine. It's just these even roots that we worry about. In order to deal with that, in order to deal with negatives under square roots, what we do is we take anything inside of an even radical and we set it greater than or equal to 0 and solve the inequality. I'll write it down. So as an example, we were using the function the square root of 7x plus 5 in our previous example. We take the inside and just the inside, all right? We just take the inside. We don't take the radical, just the inside. 7x plus 5, and we set it greater than or equal to 0, right? Because the inside of a radical can be 0, that's okay. We just need the inside to be 0 or greater. So this says make sure that the inside is 0 or greater. And then we solve this inequality. So we would subtract 5 off both sides. You would get 7x is greater than or equal to negative 5. Then we would divide both sides by 7. We get x is greater than or equal to negative 5 over 7. This means that I can plug in any number greater than or equal to negative 5 over 7 to this function and not run into any problems. Greater than or equal to, or equal. So that's our first part. No x value should create a negative under an even root. So we set the insides of radicals, even radicals, greater than or equal to 0, solve the inequality. The other big issue that we have is with making the denominator equal to 0. So no x value in the domain should make the denominator equal 0. Oftentimes, what this is going to mean is factoring the denominator and then taking those x values out of the domain. So for example, let's say we had something like g of x is equal to 2x all over x squared plus 8x plus 15. I'm going to take this denominator and factor it. So x squared plus 8x plus 15 factors into x plus 5 times x plus 3. When we do this, this helps us see what values will make the denominator 0, because the only values that will make this denominator 0 are the values that make either one of these factors equal to 0. So we'll take each factor and we'll set it equal to 0. X plus 5 equals 0. Subtract 5 on both sides. X is equal to negative 5. X plus 3 equals 0. Subtract 3 on both sides. X is equal to negative 3. So these two values, negative 5 and negative 3, need to be removed from the domain. Sometimes it's easier to look at this if we draw ourselves a number line. And in fact, I like to draw myself number lines all the time. So if we draw ourselves a number line, negative 5, negative 3, you don't need to make this super pretty, right? You don't need to draw all the tick marks, just negative 5 and negative 3, make sure they're in the right order. I need to make sure that they are removed from our domain, right? Our domain was going to be everything. It was going to be negative infinity to infinity, but I want to not take negative 5 and negative 3. So what we're looking at taking are all the numbers besides that. In interval notation, negative infinity is down here, positive infinity up here. In interval notation, this right here would be the interval negative infinity to negative 5. We take negative 5 out. Then we go from negative 5 to negative 3. That's this portion right in here. So negative 5 to negative infinity right here. Parenthesis to exclude negative 5. Parenthesis excluding negative 5. From negative 5 to negative 3, excluding. And then from negative 3 to infinity. That would be the domain of this function in interval notation. The big important thing is that negative 5 and negative 3 are excluded values. They are not in the domain of our function. Every other number is, except for negative 5 and negative 3. So let's go ahead and do a few examples. Again, remember, when we start these problems off, we are thinking to ourselves, the domain is everything. We're just looking for two things. We're looking for radicals. We're looking in the denominator. So I'm looking at this first problem. I ask myself, is there an even root? Is there a radical at all? No, no radical. Okay. What about x's in the denominator? Are there any x's in the denominator? No. That means that there's no problems that we have to look for here. This guy, he has a domain that's everything. So his domain is going to go from negative infinity to positive infinity. Includes all real numbers. We'll look at the next one. We ask ourselves for part B, are there any radicals? Nope. Okay, then the only thing we're worried about is that denominator. So we are going to factor the denominator. We can factor out an x. It factors into x times x minus 9. So the values we want to exclude are x equal to 0. And so normally we would write x minus 9 equals 0, and then we would add the 9 to the other side. I'm going to go ahead and skip the part where I write this step down. Normally you would write it and then move the 9 over, but really you start to do this mental math really quickly, where if you see x minus 9, and you set that equal to 0, you can see that that's going to be 9. And you can do this also with other factors. X plus 5 equal to 0. If you just see x plus 5 in a factorization, times, let's say 2x minus 7, I just look at the opposite sign. So x plus 5 equal to 0 is going to give me x equal to negative 5. Something like 2x minus 7, when I set that equal to 0, is going to be x equal to 7 halves. And the math I'm doing in my head when I do that, 2x minus 7 equal to 0, I know I'm going to add the 7 over. So I know that the sign of my answer is going to be the opposite of the 1 inside here. So I would add that 7 over, 2x equals 7, and then I know that the next step after this would be dividing by the coefficient. So what I'm doing in my head, I'm making this the opposite sign that I see, and then dividing by the coefficient. So if you had 3x minus 2, and you wanted to set that equal to 0, if that was part of a factorization, this right here would be positive. Let's actually do positive here. Do plus 2. The answer here would give you an x equals negative, because the positive, when you subtract from both sides, will become negative. Negative 2 divided by this coefficient 3, negative 2 thirds. Anyway, that's all just an aside. That's the mental math for factoring. Here, back to the problem, these are the values we want to exclude. Right? We want to exclude 0 and 9. So on a number line, 0, 9, I am excluding these values. I'm excluding those values. As an interval, the first part goes from negative infinity to 0. Union, the next part is from 0 to 9. Union. Then the last portion of this goes from 9 to infinity. And that will be our domain for this function. For this next function, part C, we have h of x is equal to 5x squared minus the square root of 2x plus 1. There's no denominator to worry about, but we do have a radical involved. Now, we don't really care what's happening outside the radical. That's really none of our business. We do care about what's happening inside the radical. So we need the inside of this radical to be positive. Now I'm going to take the inside of the radical, which is 2x plus 1. I don't keep the radical. I get rid of the radical. I just keep the inside. And I need that to be greater than or equal to 0. I can subtract 1 from both sides. So I have 2x is greater than or equal to negative 1. Divide both sides by 2. I get x greater than or equal to negative 1/2. As a number line, so we were going to put it on a number line so that we can write it in interval notation. I'm going to plot negative 1/2 here. This is greater than or equal to negative 1/2. So sometimes we use circles like this, and sometimes I will use brackets. At this moment in time, I haven't made an interval notation video, but I have a high probability of making one immediately after this. So by the time you're watching this, there might be an interval notation video already up. I will probably do that immediately after finishing this video. Anyway, we use a bracket because this is a greater than or equal to, and it's everything greater than that. Everything greater than that. So as an interval, this is the interval negative 1/2 to infinity. All right. For this next problem, there's two issues here. All right, there's two issues. 1, radical. 2, that radical is in a denominator, and that that gives us a really specific case. Normally with radicals, we set the inside greater than or equal to 0 because the square root of 0 is 0. There's nothing wrong with having the square root of 0. However, there is something wrong with 1 over the square root of 0 because 1 over the square root of 0 is 1 over 0, which is an issue. We don't want that. So when we have radicals in the denominator and we're trying to find the domain, we need to set the inside of the radical strictly greater than 0 instead of greater than or equal to 0. So I'm taking 6 minus 5x, and I am setting it strictly greater than 0 because I don't want the inside to be equal to 0. I need it to be greater than 0. I'm subtracting 6 on both sides, so I have negative 5x is greater than negative 6. And I'm going to write out the algebra of the next step because it's important. I'm going to divide by negative 5 on both sides here. That will cancel these negative 5s out. When I do that, when I divide by a negative and I'm solving an inequality, it flips, right? It flips the direction of the inequality. So it goes from being greater than to being less than. Negative 6 divided by negative 5 is 6/5. So x is less than 6/5. I'm going to draw out a number line. 6/5 will go right here. And we are less than 6/5. Less than 6/5. So the domain of this function, w of x, goes from negative infinity to 6/5. I can plug in any number between negative infinity and 6/5. Finally, let's look at part E, which is definitely a difficult one because there's a few things going on here. In part D, we didn't worry about the numerator because the numerator isn't part of the denominator, for one, and two, the numerator didn't have a radical in it. Here, we have a radical in the numerator, and then we also have denominator stuff to deal with. So we have to take care of both issues. There's two issues we have to take care of. So the first one, the denominator, right? We can't have any zeros in the denominator, so we're going to set negative 3 plus 2x equal to 0. Adding 3 over, we get 2x is equal to 3. Divide by 2, x is equal to 3 halves. This number, x is equal to 3 halves, needs to be removed from our domain. Right, so I'm going to put a big circle here on 3 halves so I know I'm excluding it. The other issue is that we need the inside of the radical to be greater than or equal to 0. So we need negative 1 plus x, the inside, be greater than or equal to 0. When the radical is in the numerator, you use the greater than or equal to. It's when the radical is in the denominator that you use strictly greater than. Right, so I add 1 to both sides. I get x is greater than or equal to 1. So we're looking at taking all values greater than 1, greater than or equal to 1, greater than or equal to 1. Now 3 halves, keep in mind, 3 halves is 1.5. So we're keeping all numbers greater than 1 except for 3/2. 3/2 has to be removed. So that's all numbers greater than 1 except for 3/2. It's kind of like you have parentheses here. So the way that our interval notation would work for this, we would go from 1 to 3/2. We would exclude 3/2, union 3/2 to infinity. And that would be our domain. So that covers our big domain rules. Again, big idea. We're looking for radicals, even roots, and setting the inside greater than or equal to 0, unless the radical is in a denominator. If the radical is in a denominator, we're setting it strictly greater than 0. Right? That's the first thing we're looking for. The second thing is we're looking for values to exclude because they make a denominator 0. To do that, we're just factoring the denominator and finding out what values would make the denominator 0, plucking those numbers out of the number line, and the rest is the domain. And that's everything there. So I'm probably immediately after this going to go make a video that you may have already watched because I'm going to insert it right between the previous video and this one. I hope you have a fantastic day. I'm going to stop rambling. Have a great day. Enjoy the math. I'm just going to stop talking. I hope you didn't listen this long to hear me ramble. Bye.